Hello everyone. Today we are going to start a new chapter, which is chapter number 3, network frequency. Network frequency characteristics. So in this chapter, we will learn how to use second order differential circuits to build uh, low pass, band pass, low pass, high pass, band pass, and band stop filters. Okay, so in this chapter, we're gonna learn some applications of AC circuits that we introduced in the last chapter. Okay, so let's start with the concept of transfer function. Okay, so let's see an example. If we have a voltage source, Vs, an inductor, a capacitor, and a resistor, everything is connected in a series way. Okay. We can define the voltage on the voltage source as Vin, which is the input voltage, and we can define the voltage on resistor is Vout, which is the output voltage. Okay. And then the relationship of Vin and Vout is defined as the transfer function. Okay. So, in other words, Vout divided by Vin is the transfer function, and we use TF to represent the transfer function. So how to find these two variables relationship? To do that, there's a very simple relationship between these two factors, and that is the voltage division law, right? Because everything in this loop is connected in a series way. In other words, Vout equals to ZR divided by ZL plus ZC plus ZR times Vin, right? And if we know ZR, ZL, and ZC, then we can find the relationship of Vout and Vin, right? So in this example, we know the impedance of these three components. The inductance of the inductor is 1 Henry. The capacitance of the capacitor is 1/17 farad, and the resistance R is 2 ohms. Okay. All right. So ZR is the resistance itself is R. ZL equals to J omega L, right? Based on the formula to calculate the impedance of the inductor. And for capacitor, the impedance is 1/J omega C. And for the last one, ZR, the impedance is the resistance R times Vin. Okay, so now we can plug in values into this formula. R is 2 ohms divided by J times 1 plus 1/J omega 1/17 plus 2 times Vin, right? And by we can multiply J omega on both sides of this ratio, of this fraction number, and that will become J omega 2, 2J omega, and this part becomes J omega square plus 2J omega plus 17, right, times V. So now we can see the ratio of this two factor is 2J omega divided by j omega square plus 2j omega plus 17. Correct. Alright, so after we find this transfer function, we can make two plots. The first plot gonna be the magnitude versus the frequency, omega, right? Because this number is a complex number, right? It has the real part and the imaginary part, but we haven't transferred this complex number into the representations that we are familiar with, which are polar fronts or rectangular fronts. This is the complex number before the simplification, right? But you need to know that this relationship or this rational number is a complex number. Therefore, we can plot the magnitude of this complex number. And you can do that by using MATLAB. After you input this function into MATLAB and do the plot gonna be something look like this. Okay. So it has a peak point with the increase of the frequency, omega. And after it passes omega 0, this special point, when you increase omega, the magnitude actually is decreasing. Okay, so that's the magnitude plot. Another one is the phase angle, right? Because a complex number contains two elements. One is magnitude, the other one is phase angle. So if you do the phase angle plot, the plot actually looks like this. Okay, it starts with 90 degrees and it ends up with minus 90 degrees. Okay. Alright, so in general, the transfer function can be a transfer function, a TF, can be represented as a function contains j omega, and we use n j omega to represent, divided by another function with respect to j omega, right? And we can verify this general form by using this representation, right? So in this example, nj omega equals to 2j omega, right? And dj omega equals to j omega squared plus 2j omega plus 17. So the general form of a transfer function can be represented by a derivation of two functions with respect to j omega, right? And this representation can be further represented as k0 j omega minus z1 times j omega minus z2 times all the way to j omega minus zn divided by j omega minus p1 times j omega minus p2 times all the way to j omega minus pn. Okay, and z1, z2, all the way to zn, those variables are called zeros. And p1, p2, all the way to pn, those variables are called poles. Alright, so let me explain what are zeros and what are poles. Zeros, just like their names, they will make the transfer function 0, right? For instance, if j omega equals to z1, then you plug in this value into the transfer function, and the first term gonna be 0. Therefore, when you multiply 0 with other values, the final result can also be 0, right? So z1 is a 0. And for poles, poles are values that make denominator 0, right? For instance, if j omega equals to p1, and you can plug in this value into the transfer function, and you will find the denominator becomes 0, right? So we can also use this question as an example. What are zeros and poles of this transfer function, right? Let me rewrite this transfer function in the new page so we can discuss this question. Right. So let's first look at zeros. What are zeros of this transfer function? The answer should be 0, right? Because if we plug in j omega equals to 0, then the whole transfer function equals to 0. So j omega equals to 0 is a 0, right? What about poles? To find poles, we need to transfer the denominator a little bit, right? Because this from is not easily to observe. So we can change that to this from. Well, it cannot be perfectly defactorate, but let me see if we can. Yeah, it's not easy to find, but if I change this number to 1, okay, then this function becomes j omega plus 1 square, and you can find the poles of this transfer function, and that will be j omega equals to minus 1, right? J omega equals to minus 1 is a pole. Okay. Alright, so let's do an exercise to enhance the understanding of these two concepts. So let's see if we have a circuit with a voltage supply, a resistor, an inductor, and a capacitor, and everything is connected in a series way. The resistance is 5 ohms, the inductance is 1 Henry, and the capacitance is 1/4 farad. Our goal is to find the transfer function. Excuse me. The transfer function of this circuit. Alright, so just like the example we see before, we can define Vin as the source voltage, and Vout is the voltage on the capacitor. And we can also find the relationship of Vout and Vin by using the voltage division law, right? So that will be ZC divided by ZR plus ZL plus ZC. And then we just need to plug in the impedance of these three factors. For the impedance of capacitor, that will be 1/j omega times 1/4, and the impedance of resistor is 5 ohms plus j omega times 1 plus 1/j omega times 1/4. And again, we can multiply j omega on both sides, and that becomes 4 divided by 5 j omega plus j omega square plus 4. Right, from here to here, what I did is I multiplied j omega on both sides of this function. Alright, so now the bottom part can be rewritten as j omega minus 1, right? I'm sorry, j omega plus 1 times j omega plus 4, right? And now we can easily recognize what are zeros and what are poles. So zeros of this transfer function are none, right? Because there's no j omega on the top side, on denominator of this transfer function. But we can find two poles. As I mentioned before, poles are numbers that make the denominator 0. So we have two numbers that will make the denominator 0. They are j omega equals to minus 1 and j omega equals to minus 4. Correct. Right, so this example shows how we find the transfer function. Transfer function actually is a very important concept we need to introduce before we introduce filters, right? So after we know this concept, let's look at 4 specific filters. But before we do that, let me first give you the definition of filters. Filters are defined as a network that is designed to pass signals with a specific frequency range. Okay. And reject signals outside range. I will explain this definition later, but let's first take a look at the simplest filter, which is the low pass filter. Okay. The configuration of the low pass filter is a RC circuit. We have a voltage supply, we have a resistor, and a capacitor. By the way, this is this is an AC source. Okay. Capacitance is C, resistance is R, right? And we define the output voltage is the voltage on the capacitor. Alright, so just like the example I introduced before, we can find the transfer function of this RC circuit, right? And that will be V out divided by V in, which is Vs. And that equals to Zc divided by Zr plus Zc, based on the voltage division law. And then we can plug in values of Zc and Zr. Zc equals to 1 over j omega c. Zr equals to R plus 1 over j omega c. That's the denominator, right? And here we can do the same thing. We can multiply j omega c on both sides, and this number becomes 1 over j omega cr plus 1. Right. Alright, so that's the transfer function we need. And then we can do the plot. We can find what's the magnitude of this transfer function. To find the magnitude, we can, since this is a fraction number, the magnitude of a fraction number equals to the magnitude of denominator divided by the magnitude of numerator divided by the magnitude of the denominator. So that becomes 1 divided by the magnitude of j omega r plus 1. And as you can see, the denominator is a rectangular form, complex number. So the magnitude actually equals to the real part square plus j omega r, the imaginary part square, and then take the square root, right? So that's the magnitude of the transfer function. And then we can also find what's the phase. What's the phase angle? The phase angle equals to, we use phi omega, this Greek letter, to represent the phase. And that equals to what? Equals to the phase of denominator. Let me use phi n omega to represent minus the phase of denominator, right? And in this transfer function, the phase angle of denominator is what? Is 0, and the magnitude, the phase angle of denominator is tangent to the power of minus 1 over omega cr, right? I'm sorry, the inverse of that. Imaginary part divided by the real part, right? Alright, so let's show the plot of these two variables. Let's first find the plot of the magnitude. To do the plot, you can use MATLAB, and that will automatically give you the plot. But let's say if you don't have the MATLAB, we can also finish this job. So we can analyze some special points. When omega equals to 0, right? When omega equals to 0, then the magnitude equals to 1 over square root of 1 plus 0, and that is 1. So the magnitude starts at 1. And when omega equals to, this time let's say an special point, which is 1 over RC. And this time the magnitude becomes 1 over square root of 1 plus 1 square, and that is 1 over square root of 2, that is square root of 2 over 2, right? So the magnitude is square root of 2 over 2 when the frequency equals to 1 over RC. And let's look at the last point, which is when the frequency equals to positive infinity. At this point, the magnitude equals to 1 over square root of 1 plus positive infinity square, and that becomes 0, right? So the plot of magnitude gonna be something like this. It starts with 1, it goes down to square root of 2 over 2 when omega equals to 1 over RC, and it goes down to 0 when omega is positive infinity, right? And also we can do the plot of phase angles. When omega equals to 0, the phase angle equals to 0 degrees. And when omega equals to 1 over RC, the phase angle becomes minus 45 degrees. And when omega equals to positive infinity, the phase angle becomes minus 90 degrees. Okay. You can plug in these three special points into this function, and you can find the corresponding phase angle values. Alright, so why we can call this circuit or this transfer function as a low-pass filter. So here we need to go back to the definition of filters. A filter is defined as a network that is designed to pass signals with a specific frequency range and reject signals outside of the range. So let's look at this diagram. when the frequency is in the range from 0 to 1 over RC, the corresponding magnitude values are above square root of 2, square root of 2 over 2, which we can define as high magnitude, right? And when the frequency passes this special point, when the frequency is in the range from 1 over RC to positive infinity, the magnitude is below square root of 2 over 2, this threshold, and we can call it as low magnitude, right? So what that means? That means if you have an input signal in the range within 0 to 1 over RC, then the frequency can pass this filter because the magnitude is high, which means you can imagine this low pass filter as a switch, as an adaptive switch. This switch will reject low frequency signals. It will accept low frequency signals and it will reject high frequency signals, because when the frequency is above 1 over RC, then the switch is off because the magnitude is very low. But before that, the switch is on because the magnitude is high, right? So that's the mechanism of the low pass filter. And we call this 1 over RC as the cutoff frequency. Cutoff frequency describes the characteristic of this low pass filter. You can use this characteristic to design different low pass filters to fit different applications, right? All right, so let's look at the other one, which is very similar to this low pass filter. It's called high pass filter. A high pass filter uses the same circuit with the low pass filter. It is also an RC circuit, but this time the difference is we put the output voltage on another component, which is the resistor. Okay, so this time the transfer function becomes V out over V in, and that is ZR divided by ZC plus ZR, right? Because this time the output voltage is cross resistor instead of the capacitor. So we can plug in the values of impedance of these two components. ZR is R, ZC is 1 over J omega C plus R, right? After you simplify this expression, you got J omega C R over 1 plus J omega C R. And in the same way that we did in the previous filter, we can find what's the magnitude of this transfer function. And that will be the magnitude of the top side and the magnitude of the bottom side due to the division operation, right? And that is what's the magnitude of the top side? That will be 0 square, right? Because we don't have real number part, plus omega C R square and take the square root. That's the imaginary part. And for the bottom, the real number is 1 square plus omega C R, that's the imaginary part square. Sum them together and take the square root. So after simplify this expression, the final result is omega C R divided by 1 plus omega C R square. Okay. And you can also find what's the phase angle expiration. That is 90 degrees, because the top side of the top side, the phase angle of the top side of this complex number is 90 degrees, minus tangent to the power of minus 1 omega CR divided by 1. Right, so let's make the plot of the magnitude. And you can also choose two ways. The first way is MATLAB, right? And the other way is we can analyze some special points. The first point is when omega equals to 0, right? The initial point. When omega equals to 0, then the magnitude equals to 0 divided by 1, and that is still 0. Which means this time the plot starts with 0. Okay. And when omega equals to 1 over RC, we can plug in this value. Magnitude equals to 1 over square root of 1 plus 1 square, and that is still 1 over square root of 2. Right? So you start with 0 when omega equals to 0. And when omega equals to 1 over RC, the magnitude becomes square root of 2 over 2, which is 1 over square root of 2. And when omega equals to positive infinity, the magnitude becomes 1 at the positive infinity divided by 1 plus positive infinity square, and take the square root. Alright, so for this one, we can analyze the trends of numerator and denominator. So that becomes positive infinity divided by 1 plus positive infinity is still positive infinity. And when you take this square and then take the square root of positive infinity, the bottom part is still positive infinity, and that is just 1. Which means when omega is positive infinity, the plot is approaching 1, right? It has a limitation. It doesn't like the exponential function which which grows without limitation, without boundaries. We have a limitation, and that is 1. Right, so why this circuit can be called high-pass filter? Because if you look at the frequency range from 0 to 1 over RC, the magnitude is low. In other words, if you treat the filter as an adaptive switch, the switch within this frequency range is off, is closed, is open, right? And above 1 over RC, the magnitude becomes high, which means the switch is open, the switch is on, the signal can pass the filters, can pass this filter, right? So as you can see, this filter reject low frequency component and accept high frequency component. So this is why it called high pass filter. Right. All right. Let's introduce the last two filters. What's time now? Yeah. I think I can finish that within 10 minutes. Okay. The last one is called band pass filter. And for the bandpass filter, we use second order differential circuits, which means we use RLC circuit. Right. And the output is the voltage on the resistor. The input is still Vs. So just like the other two filters, we can find the transfer function of this signal, of this circuit, and that will be ZR divided by ZL plus ZC plus ZR, and that equals to R divided by 1 over J omega C plus J omega L plus R. Right, so I swap these two variables. All right, and then we can multiply. We can multiply. No, this time let's make a little bit different. Let's change 1 over j omega c to minus j over omega c plus j omega l, because 1 over j omega c equals to j times j omega c, which is j over omega c times minus 1, right? Because j squared is minus 1 plus r, right? And now this transfer function becomes r divided by r plus j times omega l minus 1 over omega c. Okay. All right, so that's the transfer function. And then we can find the magnitude of this transfer function, and that will be r. The magnitude of the top side is just r, right? Because it's just a real number. For the bottom side, that will be r squared plus omega l minus 1 over omega c squared. And that becomes, we can multiply omega c on both sides of this fraction number. But notice that when you multiply omega c, inside the square root, that becomes omega c squared, right? Omega c r squared plus omega squared LC minus 1, right? And that's the magnitude. All right, so now we can do the plot of the magnitude. In the same way, we analyze some special points. When omega equals to 0, right, then the magnitude is 0, because the top part, the denominator, becomes 0, and that will make the whole thing 0. And the second point is when omega equals to 1 over square root of LC, what will happen? The magnitude becomes r 1 over square root of LC times C divided by square root of CR over square root of LC together square plus 0, right? And that is RC over square root of LC divided by RC over square root of LC, and that is just 1, which means this plot start with 0, and when omega equals to 1 over square root of LC, the magnitude is 1. And what happens if omega equals to positive infinity? Then the magnitude becomes positive infinity divided by the square root of positive infinity square plus positive infinity square, and that is what? So we can analyze the trend of these two parts, or you can do a simple calculation. You can do positive infinity divided by 2 no, we need to analyze the trend, right? Yes, we can find the bottom part actually is increasing faster than the top side, which means when omega equals to positive infinity, the magnitude becomes 0 again, right? Right, so the plot of this magnitude is it starts with 0 and it goes to 1 when omega equals to 1 over LC, square root of LC, and it goes back to 0 again when omega equals to positive infinity. Okay. Alright, so some people may ask, what about cutoff frequencies, right? Does the bandpass filter also have the cutoff frequency? The answer is yes. When you find cutoff frequencies of this filter, there are actually two cutoff frequencies. Let's go back to the previous two filters. For the high pass and the low pass filters, when the magnitude equals to 1 over square root of 2, the corresponding frequency is defined as the cutoff frequency, right? And the same thing for low pass filter. When magnitude equals to square root of 2 over 2, the corresponding frequency is the cutoff frequency. So this principle can also be applied on the bandpass filter. When the magnitude equals to 1 over square root of 2, there are actually two corresponding frequencies. The first one is called low cutoff frequency. The second one is called the high cutoff frequency. And how to find these two cutoff frequencies? You need to solve the equation. In other words, you need to solve what are frequency values when magnitude equals to 1 over square root of 2, which means you need to solve r omega c divided by square root of omega c r square plus omega square LC minus 1 equals to 1 over square root of 2, right? And by solving that, you can find two solutions. One is smaller than the other one, and the smaller one is called the low cutoff frequency, and the expression is minus r over L plus square root of r over L square plus 4 1 over LC, okay, divided by 2. And the second one, the high cutoff frequency, equals to minus r over L. I'm sorry, that should be positive r over L plus the square root of r over L square plus 4 times 1 over LC divided by 2. Okay. So the first one is called low cutoff frequency. And the second one is called the high cutoff frequency. Okay. And the middle one, the middle point between low cutoff and high cutoff is the center frequency, which is also called the center frequency. And that is 1 over square root of LC. Okay. Alright, so let's end up here. And in the next class, we're gonna introduce the last filter, which is the band reject filter. And we will also give the corresponding concepts of bandpass and band reject filters. Alright, I'll see you guys next time.